some more about the lab, and then we'll start that. So we'll just do the synthesis lab continued here. So from last time, what we're going to do is we're going to heat it up, and then we're going to cool it in an ice bath. And what we want to do at this stage is we want to precipitate out these. So let me get the correct formula for this. This is usually lowercase here. There's some waters of hydrate. How many waters of hydrate are there in this? That's usually determined. What you can do is you can dehydrate it and then see how many waters we end up with. And this compound is going to have, let's see, 3 waters of hydrate. That's what it looks like. And that depends on the lattice and other factors. So we want this. And then what we're doing here is we're changing this from aqueous to an ethanol. And that's going to decrease the solubility. So hopefully we end up with K3CrOx3.3H2O solid. This is a green-black precipitate. But what we don't want to do is we don't want to make this go too far, because if we add, let's say, too much ethanol, do you know what could possibly happen? What could possibly happen is co-precipitation. And so we do not want co-precipitation. And so avoid co-precipitation with the other stuff. The other stuff is what we added excess of. So for example, we added, if you recall, we added excess oxalic acid. Oxalic acid is a white precipitate, or white PPT. And we also added excess potassium oxalate, although potassium oxalate is highly soluble. It's also white PPT. And so there's a little bit of an adjustment here. If you start to see some white precipitate, maybe it's too much. You know, it's making it too inhospitable, too ethanol-like, and not water enough. And so we need a little bit more water in that particular case. And so we want to avoid co-precipitation, which yields contamination. All right, so hopefully we generate a lot of nice crystals of precipitate here. Now, this solution is going to be contaminated. I mean, it's a mixture. So what we want to do is we want to filter out the precipitate. And so filter precipitate. The way we're going to do that is we're going to use a vacuum filtration apparatus. Let's take a look at the vacuum filtration apparatus that's shown here. And so in this particular vacuum filtration apparatus, we have this set up here. One, this is a water aspirator. Water aspirators are not used in California. This is a huge waste of water. It's cheap because you just use the sink and flowing water to generate a vacuum. But it's obviously it's a waste of potable water, and so not used. Instead, we use a mechanical vacuum pump, and so we have just this this pump. You have suction pumps, or you can have air pumps that generate pressure, but it depends on which side. If you have an air pump that generates pressure to inflate tires or whatever else, it creates a vacuum on the other side, so we can use that vacuum. And so we have house vacuum. It's pretty weak. Do you hear that? Some house vacuums are a bit stronger. Since we have a mechanical vacuum pump, we don't want to suck water into our pump, because if we suck water or any liquids are not compressible. If we suck a liquid into our pump, it's going to destroy the pump. And so we have to make sure liquids do not get sucked into the pump, and therefore we use this device here. This is a liquid trap. Here. So the idea here is if any liquid gets sucked into this is called the side arm. And do you know what this flask is called? This is called a filter flask. And it's primarily used for vacuum filtration. So when we hook up the side arm to vacuum here, and this should just pull the air. But if liquid gets sucked in here, into the side arm, it gets spit out here. Actually, this is wrong. This is backward. It gets spit out into the flask here. What? I didn't really notice that. Here, and then it'll collect it down here at the bottom. And this other tube here is up. It's kind of up here. This other tube here is cut here. That way, we can trap a lot of water in here before it gets sucked into our vacuum pump. Does that make sense? And so these are backwards because the way it was set up, it's not very effective because it just generates a little reservoir of water, which is going to get sucked into the vacuum pump and destroy our vacuum pump. So this is backwards, unfortunately. But it's okay. They probably hired a graphic artist to do this, not a chemist. But I'm surprised they didn't catch it. But that's frequently the case. This is a Buchner funnel. It's a 9 centimeter. It's a 9 centimeter diameter like this. And in Buchner funnel, there's a shelf inside here with holes in it. This. And so all you do is you lay a piece of filter paper flat in there, and then you wet it down so it adheres to the bottom and creates a seal. And so take a 9 centimeter piece of filter paper and then just put that inside here, lay it down on the bottom, and then spray it with DI water. You got to spray it with DI water because we don't want anything to get underneath that. And then we create a vacuum. I guess I don't have the demos here, but what we want to make sure is that there are no vacuum leaks. So the Buchner funnel has this rubber stopper, and we got to make sure it's tightly sealed here. And we also want to make sure this has a tight seal. These should all have a tight seal. And then we need to make sure we have a tight seal with our tap here for the vacuum, house vacuum. And then what we'll do is we're going to just kind of pour. Usually, you guys remember what the supernatant is? Supernatant versus precipitate? Yeah, the liquid layer. And so what we try to do is we try to get the supernatant in here first, the liquid. That way we avoid clogging this. And then we get the suspension in here and dump all the precipitate. And then we'll have to wash it. But the problem is we can't use water to wash it, because if we use water to wash it, what's that going to do? It's going to dissolve all our precipitate. And so we're going to wash it not with water. We're going to wash it with ethanol. Now, we also want to wash off any oxalic acid and potassium oxalate. And so we're not going to use 100% ethanol, because we got to make sure we wash that off and it doesn't co-precipitate. And so what we're going to do is we're going to wash it with this sequence here. Wash the crystals on the funnel with 3 10-milliliter portions of 50% aqueous ethanol, followed by 25 milliliters of 95% ethanol. Well, what we have is 95% ethanol. And so just dilute it in half, so if I want 3 10 milliliters, I need 30 milliliters. So I'll get 15 milliliters of 95% ethanol and 15 milliliters of water. That'll give me my 30 milliliters of wash solution. And I just use that, and then followed by 25 milliliters of 95% ethanol. The 95% ethanol is not only good at washing the residuals, 50% ethanol, but it's also good at washing water away, because water is very soluble in 95% ethanol. 95% ethanol evaporates quite quickly, so it's kind of weird. We're using ethanol to wash water off the crystals. That way the crystals dry faster. But we aren't going to air dry these in a short period of time. We're going to air dry these overnight at least. It's not long enough to dry these at the end. But the wash is important, because if we don't wash the crystals off, we're going to get contamination due to. And so, as far as the wash goes, we're going to do 3 times 10 milliliters of. It doesn't have to be exactly 50%, about 50%. Ours is going to be a little less. And then 1 times 25 milliliters of 95% ethanol. This is just get rid of most of the water. Replace it with ethanol and let the ethanol evaporate quickly. That's what we're going to do. But we're not going to stop here. Okay, we're going to add a few steps. The steps we're going to add is for recrystallization. Recrystallization is a way that we could further purify our precipitate. And so what we're going to do is we're going to take our precipitate here, of it should be our complex. And then what we're going to do is we're going to dissolve it in a minimum of water. When I say water, it's DI water. Don't use tap water, otherwise you're going to severely contaminate your crystals. So we dissolve it, and then we generate an aqueous solution. So we just want a minimum of water here to redissolve our precipitate. And then we're going to reprecipitate it out. So by doing this step, we're further getting rid of any kind of contaminants that might have made it through in there. And so how do we reprecipitate it out? The way we reprecipitate it is we add the ethanol plus ice bath. But what I'm going to recommend is in this recrystallization, we're going to add the ethanol and then just try to get some crystallization there, ice bath. And then what we're going to do is we're going to leave this, we're going to leave this in our drawer. So hopefully we get some precipitation. You don't want to maximize. Okay, you don't have to maximize precipitation. So there are different ways we can do this, you know. But anyway, I'm going to cover with watch glass. And leave it in your drawer. In the first precipitation, we want to maximize the amount of precipitate. So we're going to just keep adding ethanol to try to get the max. Cool it in an ice bath. We want rapid precipitation because we don't want to wait all day. In the second precipitation, I want it to precipitate slowly. That is, slow precipitation is what I want to, because I want to generate large crystals. In order to generate large crystals have to be fairly pure because there can't be any like defects or contaminants because that would upset how they layer or how they pack in the crystal lattice. And so if we have large single crystals, then those are usually highly pure because these large crystals lock out contaminants. Whereas if we have lots of tiny crystals, then we're more susceptible to contamination. And so here, what I mean by don't maximize precipitation is there's two processes involved in precipitation. Does somebody know the two processes that are involved when we think about precipitation? Kind of coagulation, but a little bit different because coagulation in the other sense is coagulating little crystals together to form bigger clumps of crystals. But what we want to do is we want to form big crystals, big single crystals rather than agglomerates of crystals. And so the two processes that are involved, one is nucleation, and the second process is growth. Nucleation is sometimes it's very hard to nucleate crystals, you know, because you have to get them to pack perfectly initially, and then they can grow. And so sometimes what people do is they add seed crystals, or they have surfaces like scratch surfaces or corners where the ions can stick and then grow from there. And so there are lots of things, dust particles, etc., can aid or assist in nucleation. And so the two things that we have is this. These are the two extremes. One is we nucleate lots of baby crystals. And so if we have lots of nucleation, then we're going to have minimal growth. And so we end up with lots and lots of tiny crystals. Or minimal nucleation. And so let's say we only nucleate one crystal. If we only nucleate one crystal, then that crystal is going to grow big. Ideally, we'd like to nucleate just one crystal, but that's too difficult. And we're going to maximize growth. So we can have lots of baby crystals that don't grow very big, or a few baby crystals that will grow big. We want a few baby crystals that will grow big. And so here, I'm tempted to eliminate the ice bath too, but that's okay. You could do the ice bath. We want slow growth. So I'd probably just go with the ethanol. Try to get some crystals and then leave this in the drawer to let those crystals grow. So we probably can make it through the vacuum filtration today. Any questions on the lab? No, you don't have to. The vacuum filtration apparatus is this common piece of apparatus. So you don't have to have everything in there. This is individual. Although this is individual, I'll probably have you guys work in pairs if you want for the report. You could choose whoever got the better crystals. So I was looking for a nice short video. This is a safety video. Ready for the first experiment? Time. I know. When I took my first lab, I had similar concerns, but once you understand the logic behind these rules, it'll be a lot clearer. Don't you think, though, that a lot of these rules are a waste of time and you slow us down? Don't worry about that. You can get seriously hurt, and that'll take more time in the lab. I'll walk you through it. All right, thanks.
Hey everyone! My name is Kayla, and I'll be your TA for this quarter. Let's go on into the lab. Alright, everyone, just come on in the lab. Go ahead and put your backpacks and things in the cubicles, that way no one will trip over them. And grab your protective gear and come on to the front.
Nice glasses.
Oh, thanks. I got them from a research lab.
That's so dorky. I got one from my dad's workshop. I thought I would save a couple bucks.
I think we need splash goggles for the first part of this lab, because we're going to be using concentrated sodium hydroxide solution, and that stuff is nasty if it gets into your eye. Hey, are you guys ready to get started?
All of us. I just realized my safety glasses don't give me that protection, so I'll go get my goggles.
Okay. I'm afraid that yours aren't good either. See the bedposts? They won't protect you against the splash of liquid. You need chemical splash goggles that will give you indirect venting. Why don't you go ahead and grab another pair and come on back?
Okay.
Before we get started, I'll just point out the location of the safety equipment in the lab. Because you'll all be wearing your protective gear, you most likely won't need to use it, but it's important to know where everything is located. The eye wash is over there. Just pull the lever, and one will automatically turn on. To turn it off, just pull the lever back to its original position, and the water will stop flowing. The emergency shower is over there as well. Do you guys know how long you need to wash after exposure? Good job on reviewing the guidelines. If you get spill on you, then quickly peel off your lab coat. And if your lab coat absorbs all the spill, then you're okay. If your clothes are contaminated, then you need to get into the shower and remove them under the running water.
Seriously, I'm not taking my shirt off. Someone take pictures and put on Facebook. Don't be silly. It's not taking care of them. Yeah, you're right. I'll have to tell the teacher.
In case of a fire, we have an extinguisher and a fire blanket over there. Use the fire blanket to smother a fire, especially if it's on someone's clothing. Or you can also push that person into the emergency shower and turn it on.
Kayla, can you show us how to use a fire extinguisher? I've never actually used one before.
In the case of a lab fire, it would be better if you evacuated the lab and let us worry about it. The safety of people is much more important than the safety of the equipment or the lab. And we do have fire sprinklers. But in any case, it's important to know how to use a fire extinguisher in a few cases where it might be needed. First, you pull the pin that locks the mechanism. Then, stand 6 to 8 feet from the fire and aim the nozzle at the base of the fire. A common mistake is to aim at the flames, but you need to aim at the fuel. Squeeze the lever to release the chemicals and sweep it from side to side. An easy way to remember is the acronym PASS: pull, aim, squeeze, and sweep. Remember that if we need to evacuate the lab, then everybody needs to gather outside so that we can account for all of the students. And do you guys have any questions? All right. In this lab, we'll be working on various individual experiments, so make sure you read all the bottles of reagents carefully before you start using them, okay?
I always get confused about the order of addition. Is it water to acid or acid to water? I never understood it.
It's easy to remember if you know the reason. The problem is that the reaction between concentrated acid and water can be very exothermic. When water is added to the acid, the reaction is so vigorous that steam forms. The steam escapes and will cause the splashing of the concentrated acid. Adding acid into the water changes the situation. Since concentrated acid is denser than water, it sinks into the water and is immediately diluted.
Now I get it. Thanks for your help.
Dan, are you going to be available? Looks like we're just about up. I'll run to the stock room and get some more. Morning, Professor. Yeah?
Hey man, how's that going?
It's going pretty well. I'm just on my way out of the stock room to get the illustration hall.
Okay, you know, I think you're missing something. Let's go back and,
Okay.
you know, Andrew, it's much safer to transfer balls using the second lift because it offers better protection in case the ball falls across.
Okay.
Oh, and don't forget to take off those gloves before you do that.
Sounds good, Professor. Yes.
Hey, Nathan.
Hey, Professor, how are you?
Good. Hey, why aren't you wearing your safety glasses?
Oh, sorry, they just caught up with them.
I know you didn't mean to do it on purpose, but what if your neighbor drops an urine on you and the gas goes flying towards you? It's pretty dangerous. You need to clean your safety glasses, just go outside, clean them, and come back in. Also, I noticed you're working too close to the edge of the hood. You know, this is not safe practice. Can I show you why? All right. Look at the dry ice ball. You see how it behaves when the dish is close to the edge, and especially when the sash is wide open? Now, think about all the hazardous vapors that will escape into the lab. However, pushing it into the hood about 6 to 8 inches and bringing the sash down makes a big difference. Plus, it better protects you from both hazardous vapors and flying debris if something goes wrong with it.
Thank you, Professor. That made a lot of sense.
Hey, this isn't very safe. Can you please step down? I know I'm not supposed to fill anything up by reaching above my eye level. That's true. You definitely don't want to take a risk by spilling a solution from above. But at the same time, you may fall from this chair. A better way of doing it would be to move the burette to the side of the bench and then move it down so that you could do your work at eye level. Then when you're done, you can move it back up and push it back. Okay, that makes sense. Thanks, Kayla. You're welcome. Oh, goodness. Sorry, I was just wondering if I could borrow your calculator. Yeah, sure, no problem. Go ahead. Thanks. I don't think we're supposed to listen to earbuds in my lab.
That system is lazy. I mean, you're not going to work in the hood or anything.
Yeah, I know, it's kind of unsafe. Like, you can't hear what's going on around you, you might miss some things.
Yeah, you're right. All right, I'll stop listen to them from now on. Thanks for looking out for me.
Okay, I'll bring it back when I'm done.
Yeah, sure, take your time, no problem.
Finishing up for the day?
Yep, just getting it all my ways.
Alright, great. Do you know the copyright team of your bus?
Yes. And then finish the first one, take it off, then you just come to take off.
Perfect. Okay, well, I'll see you next lab period.
See you next time. You know, that wasn't so bad. Thanks a lot for your help. Yeah, no problem, anytime. I think it's all you're all right.
Okay, just a reminder that we have an eye wash over there, plus the safety shower, and then at each sink we have an eye wash and a handheld shower. Just there. Normally we put the waste in that last hood that's lit up there, and so if you have waste, dump it in the waste jug back there. In a normal lab, I just have a waste beaker at the lab station, so I only go at the very end, like on the video, to dump the waste. What else? Oh yeah, the dichromate is sitting outside the hood right now. I might move it inside the hood along with the balance. Okay. Just be careful of any spills. If you do spill some, I normally use a wet paper towel to wipe it up, not a dry one because I don't want to generate any dust. And so just a slightly damp, not a dripping wet, but a slightly damp towel works well. We can put the solid waste, if you have a paper towel, put it in the tray inside there, the solid waste. All right, any questions for today's lab? No. Okay, you'll need safety goggles for this lab and proper footwear. We're okay. All right, we'll go ahead and get started then. Again, this is an individual lab, but